Hello and welcome to Chemistry 4. This is a recap episode. So let's begin. So there's three fundamental particles. We've got protons, electrons and neutrons. So protons got an electric charge of +1, electrons got an electric charge of -1, neutrons have got an electric charge of 0. Okay, so not all atoms have got neutrons. We'll speak about protium in a minute. An isotope of hydrogen doesn't have any neutrons. Okay, so yeah, that's how that works. So they're basically the fundamental particles, at this point anyway. So yeah, not all atoms have got neutrons, like I've said. So we need to look at the basically things we need to look at are charge and mass. Okay, so the relative mass of these items, these particles, protons. So we just sort of take the base to be protons 1, neutrons 1. So protons, neutrons, relatively very similar mass. Electrons 1/2000, so it's almost like a negligible mass, but electrons certainly punch well above their weight when it comes to charge. For instance, as you can see, protons and electrons have got an equal and opposite Coulombic charge. It's a name for electric charge. So even though they're a lot less massive than the protons, the electrons really got, they got, it's 1.602 times 10 to the minus 19. So its positive charge is protons, and the electrons, its negative charge. Of course, electrons are the smallest charged particle, the elementary charge, because nothing smaller than that with charge exists. All right, and then similarly with mass, protons have got a mass about 1.673 times 10 to the minus 27 kilos. Electrons about 3 orders of magnitude less massive. Okay, so what we're dealing with at the beginning here is that the main things really are the atomic number and the mass number. So the atomic number is denoted by Z. So it could be a number of protons in a nucleus, which is the elemental identity. So if it's got a different number of protons, different element. It could be the number of electrons in a neutral atom. So that's a non-ionized atom. Or it could define the position of the element in the periodic table. So it does define the position of the element in the periodic table. So that's how it's actually organised in the periodic table. It's to do with the amount of electrons in the outer shell and stuff like that. So the next thing is the mass number, which is A, and that's simply the number of protons plus the number of neutrons within the nucleus. So add them both up, we're going to get the mass number. So sometimes it's just adding the same number, and sometimes you've got like loads of neutrons and stuff like that. So that's what we're going to think about now is isotopes. So atoms of the same element are not always identical. They're different atomic masses for some atoms of the same element, and this can explain maybe how sometimes in the periodic table sometimes the mass is a bit of a funny number because it's actually averaging out all the different isotopes. So if you take hydrogen, right? So the atomic number for hydrogen is going to be 1 in all cases. That's a blanket sort of statement. So the general form that we have is we've got the mass number and the atomic number. So mass number is like above, and the atomic number is below, and then the element itself is denoted by X here, is to the right. In the middle to the right. All right. So let's look at isotopes. I've actually written isotopes here twice, so that's not good. So let's just correct that a bit. Hopefully that hasn't screwed up my formatting later down the line. So we've got 3 isotopes, right? So hydrogen's got 3 isotopes. So protium, deuterium, tritium. So you can see that protium's got 1 proton there, as denoted in the atomic number at the bottom there. So we add them up. We've got 1. We've got no neutrons, so we do 1 plus 0 is 1. So we get 1 hydrogen. We can see that with deuterium we've got you can see that we've got the atomic number is 1. We've got 1 neutron, so 1 plus 1 is 2, so we've got 2 hydrogen. We can see with tritium, again, the atomic number is 1. We've got 2 neutrons this time, so we add up the protons and the neutron. 1 plus 2 is 3. 1 hydrogen is tritium. Okay, so next up, for uranium, so the atomic number is going to be 92. Just a point here is to make out the atomic mass number. So you could say atomic mass, atomic number. But yeah, it probably makes a bit more sense to say mass number. A. and A, it's obviously A, isn't it? So that's the one on top. The Z is at the bottom. It's like a alphabetized from top to bottom. So in the case of uranium, it's commonly 235 or 238. So there's different ways you can write. You can do U-235 and U-238, like I can see there. Or I could have uranium-235, uranium-238. Or you could do that like that. 235 and then the U like that underneath, 238 and then the U underneath. Obviously, they're a little bit closer, but obviously I'm working with lines here. I'm not going to be able to get like increments. It would probably be like halfway. The middle of the numbers there would be on the actual line itself in reality. But I've done the best I can considering the format I'm using and the formatting that I'm using. So yeah. So let's look at how to find the composition of neutral atoms. So we're dealing with neutral atoms at this stage. We're going to talk about ionized atoms in a moment. So neutral atoms are U-235 and U-238. The following is done. Okay, so we can see I've just put that down again one more time. So we can see that straight off the bat we're going to know that for uranium there's 92 protons. So we know that straight away. We also know that the number of electrons in a neutral atom is going to be exactly the same. So it's going to be 92 as well as it's a neutral atom. And then simply to do find the number of neutrons, we simply do the mass number, which if you recall is protons plus neutrons, minus the atomic number, which in this instance we're going to be looking at the number of protons. So basically the protons cancel each other out and the neutrons are remaining, which is 143 in the case of U-235, and in the case of U-238 it is 146. Okay, so that's fairly self-explanatory. So one positive silver ion, one electron equals one atom. So ions are how reactions occur via ionization energy. So this is how we're going to get some reactions and more kind of, compounds and mixtures and all this sort of stuff. Well, compounds actually. Mixtures don't tend to have reactions. But yeah. So number of electrons in a positive ion is going to be Z minus the charge on the ion. So if we take, so basically we can say, so here we'll exchange in for Z the number of electrons in a neutral atom. So the number of electrons in a positive ion is the number of electrons in a neutral atom minus the positive charge on the ion. So minus plus, which is going to be minus. And yeah. Well, that's probably not the best way to look at it actually, because I could just say plus minus, but it's not really. Basically you just subtract the charge. So you subtract the charge if it's positive ion, and you add the charge if it's a negative ion. So yeah, so you could see that as some kind of attraction there. So in the case of magnesium, the atomic number is 12. So it's going to be, it's 282. So yeah, so that's going to be 2 in the outer shell, so it's group 2. So therefore, when we look in the ions, it's going to be 2 plus ions there. So let's look. So I mean, for a magnesium 25 atom, it'll be fairly similar. Protons 12, electrons, neutral atom is 12. Neutrons going to be mass number minus atomic number. 25 minus 12 is 13. 12, 12, 13. So there's neutral. But if we've got a double charge ions, we get them involved. We can see, right? Protons still going to be 12. Neutrons still going to be 13. But the electrons, we have to put in this new kind of new equation that we've got here, and we can look at the charge. So we get the number of electrons in a neutral atom, which again is going to be 12. But this time, because we've got a positive ion, we subtract the positive ion, get rid of that ion to get 10. So we've got 12 protons, 10 electrons, and 13 neutrons. So you can see we've got less electrons than with a neutral magnesium 25 atom. So similarly for these two as well, we've got potassium 40 as a K plus ion. So it's going to be a very similar sort of thing. It's group 1. And the Z is 19. So what's that? 2881 maybe? Yeah, I think so. So group 1. So 2, 8, 2, 10, 18, 19. Yeah. Okay. So protons 19, obviously. Neutrons again 40. Mass number minus atomic number 40 minus 90 is 21. Yep. And again, we're just going to subtract the charge. This time is 1 and 18. And just to see the reverse case, in chlorine 37, that's group 7. So the atomic number is 17 there. So what's that? 287, yep. So it's group 7. It's got a negative ion. And yeah. So protons again 17. Obviously neutrons are going to be mass number minus atomic number minus number of protons, just cancelling out the neutrons, cancelling out the protons rather, to leave the neutrons. It's going to be 20. And because we're dealing with a negative ion, we want to add on the ion to to see how, not, it's probably not equilibrium, but it's more, more stable anyway. So yeah, electrons. So it's basically, yeah, just take the number of electrons in a neutral atom, which is 17, add on that charge, and we get to 18. So that's all I really want to talk about this time. So I've recapped sort of the first three things in chemistry, and until next time, I guess, thanks for watching.